we're going to jump straight into a few practice questions, right? So like I said, one thing I would highlight you should know quite well is also the Gibbs free energy change, and also potentially Hess's law questions as well. You can get some variation of Hess's law, etc. in year 12, but it will be more likely to be a Gibbs free energy change question, etc. Before I even jump into questions, Taha, combustion reactions. Tell me about their entropy and their enthalpy. What do they tend to be for a combustion reaction?
They tend to be a positive entropy and a negative enthalpy.
Good, right? Both the drivers in a combustion reaction, you will usually favor the reaction going to completion, right? So you're right. What about photosynthesis, Shashank? It's specifically named in your syllabus, hence why I'm bringing it up.
It's endothermic, so enthalpy would be positive and entropy, I think it's negative.
Yeah, so you have to realize the reason the syllabus even brought that question up for you is because combustion and photosynthesis represent extremes of the spectrum. One reaction which is very spontaneous as soon as you provide it with activation energy, which is your combustion, and your photosynthesis always needs a continual input of energy. And this is usually in the form of UV, for example. Okay, good. Let's jump straight into a practice question. Some of these questions are from your exam, so you've actually seen these before. So we'll go to a question that you've not seen before, right? How about we start with, okay. So since it's a graph question, we're going to verbally go through it. I'm not gonna get you to write this down in the interest of time, right? But Taha, what point in this system did we reach equilibrium first?
At 10.
Good. And what happened at 20 seconds, Millith? What was the stimulus at 20 seconds and why?
We can see that HI was removed, and we know that because the concentration sharply drops.
Good, right? So we notice that the HI has been removed only because one of the products had their concentration sharply decline. Very good. And then we see this counteraction phase. Now, usually it should be more gradual than this, but you can see it's sharply corrected itself and it's returned back to equilibrium. Very good. What about the change at t equals 35 seconds, Shashank? I know it's a bit of a funky graph. It wouldn't look like this, but
It'd probably be something to do with temperature.
very good. Right? Good. And now you don't know whether this is exothermic or endothermic, so you can't really comment on what was actually done for this reaction here. But in HSC, you could have to infer that. So Anthony, what would you put your money on for this reaction? Is it exothermic or endothermic? If you had to guess based on first principles.
I would say endothermic.
Now you have to go back to bonds, everyone. When you break bonds, do you have to input energy or do you need to release energy?
Release.
Input.
Right? If you want to break something, you need to input your energy into it. Whereas when a product is formed, it's formed through violent particle collisions, and in the process we release other forms of energy. So the logic here is synthesis is usually an exothermic reaction, decomposition is usually an endothermic reaction. So let's assume this is exothermic. What has been done to this system if we know it is exothermic because it's a synthesis reaction?
The temperature would have been increased.
There you go, right? So the shortcut right there is you just put heat as one of the products. You just add heat here, and you know that HI has decreased, so you have to go away from HI, and the only way you can do that is by increasing heat. So very good. So we answered that question in a couple of seconds. Very good. All right, you've done these questions before, so we might go to this one. Now, this one, what I'd like you to do, if you can, maybe we'll do the next one. We'll go here. Okay. If you have a touchscreen device, for example, screenshot it and draw it. Otherwise, you can draw it in your book, but try to be as accurate as you can, because that's going to be the learning point of this question. Okay, just how accurate you can be. So raise your hand once you've finished graphing this question. Okay. I'm going to be very nitpicky because in your HSC with these graphing questions, you need to be very accurate with what you show with the initial phase, the counteraction phase, etc. So aim to get full marks for this. Okay, 30 more seconds and I'll start clicking on people. Okay, let's start going through this. So we've been told at 30 minutes, additional CH4 was injected into the vessel. Now, Taha, whenever you're drawing these concentration time graphs, what are the two phases you should be thinking of? Okay, if you're unsure about the phases, tell me this. We've added additional CH4 and its concentration has now increased all the way to 2 moles per liter, right? So all the way up here. What happens next is according to Le Chatelier's principle. So how will all the concentrations change? So when we decrease CH4, what level did you decrease it to in your graph? So it's at 2 moles per liter right now. You know it's going to decrease because Le Chatelier's principle predicts this. What level did your CH4 decrease to?
1.88.
Yeah, so it's in this question, 1.88. But the principle here is that it's a partial decrease in concentration, which is what I was trying to get at all of you, right? First thing you need to show is there's a partial decrease in concentration. The next thing that I want to really highlight is whenever you're doing your concentration time graphs, you should always think of it as two phases. There is always an initial stimulus phase, and there is always a counteraction phase. Anthony, which phase obeys Le Chatelier's principle?
The counteraction.
Very good, right? And so what does that mean for the change in concentration? It must occur according to, Shashank?
The stoichiometric ratio.
Very good, right? If you remember these two principles, you'll be fine. There are always two phases, and it's the counteraction phase that obeys LCP, and it's always a partial change. So remember, it's a partial change, right? And it's always according to the stoichiometric ratio, only the counteraction phase. Because that's literally the three most important things you should remember. And you can answer every question, right? All right, so your CH4 decreased to from 2 to 1.88. What does that mean for the change in concentration of H2 and C2H2? So I guess the first thing you want to do is, Arik, before you answer my question, what would you like to do for your approach? You've got these chemicals. Do you have a chemical equation?
You would have to write your chemical equation.
Good, right? Because you want to know what the ratio is. We don't even have a chemical equation. So what is a chemical equation?
It's CH4. Then it creates CH2 plus H2. I think. Yeah.
CH2. Good. I'm sure you're very specific. All right. So how do we balance this? Can we balance this?
Yes.
Anthony, I've asked you too many times. Ayan, balance this for me.
Okay. I would put a 1 second.
Milith, balance it for me.
2 in front of the CH4 and 2 in front of the H2.
Good, right? So now we have the ratio. It's a 2 to 1 to 2. And so Milith, this change from 2 to 1.88, right? That represents a 0.12 moles per liter change in concentration. That represents a...
Wait, it's a 3 in front of the H2.
Yeah.
Is it 3? Yeah.
Yeah.
Yeah, because it's 8 and then, yeah. Right, thank you. That's very important because if you got the ratio wrong, you got this question wrong. So having a look here, this change of 0.12, that represents how many parts of our chemical reaction? 2 parts, do you all agree? So a 1 part change should be a 0.06 change, and a 3 part change should be a 0.18 change in concentration? Good, so everything must obey that change in your concentration, right? So what that means, your H2 must increase by what amount, Taha? What should it increase to?
0.18.
It should
Oh,
increase by
increase.
0.18. What does it increase to?
It's 1.38.
Good, right? So you want to go all the way up to about 1.38. And remember, it has to form equilibrium at the exact same time point. And what about the CH2? Or C2H2, sorry. What should that do?
0.46.
Yeah, and is that increasing or decreasing?
Increasing.
Yeah, very good. So, sorry, I need to be more accurate. So this is 0.5. We said 0.46. So it should go to about there. And this is why it would be good if you had the graph paper for this as well.
So it's C2H4 ethene, and that's why it's a 2 in front of the H2.
C2H. Is it? It says it's ethine gas though.
Oh, okay. I read it wrong. That's why.
Yeah, so this is ethine gas rather than ethene. Good. All right, so coming back to this, we formed our first equilibrium and we've abided by the time, so you want to always tick that. We've abided by all the concentration changes. Now what happens is at 60 minutes, so we will draw a straight line all the way to 60 minutes. So make sure you draw a full straight line all the way to about this point and this point. So I'll just do that with you. So you should be doing that now. We add a catalyst. Serene, what is that going to do to the concentrations of all these substances? Addition of a catalyst.
Nothing change.
Exactly, good. So you literally just keep following the straight line, right? So no change at all. So let's see what else happens at 80 minutes. So the next change is at 80. So you want to drag this line all the way to 80 for all of the curves. Drag it, drag it. Okay, and now what's happened is the volume was suddenly doubled. So Arik, what are you going to do to all of these concentrations?
It's gonna go vertically up. They're all gonna.
Shashanth, your turn.
It'll get halved.
Good, right? So does that obey the stoichiometric ratio, Shashanth? Do I need to look at the ratio and decrease it all by the same amount?
No, you just halve it.
Very good, right? So remember, the initial stimulus phase just obeys logic, not Le Chatelier's principle, right? So if you double the volume, you halve the concentration. So you want to halve all the concentrations. So 1.88 should halve all the way to, is it 0.9, what is it, 0.94? 5, something like that. So put it in your calculator or do it mentally and decrease it all the way down. I'm going to use different colors so I don't confuse us all. So we're going to use CH4 in a blue color. So that decreases to, is it 0.945? No, sorry, it should be 0.94. That's it, right? Good. So we'll go all the way down to 0.94. So about there, maybe. Okay. And what's going to happen to the H2, Taha? What does that decrease to?
0.69.
It's 1.38. So no. Is it? Yeah. I think you're right. Yes. 0.69. You're right. Good. We'll decrease it all the way to there. Very good. And what about your C2H2, Anthony? What is that?
0.23.
Yeah, good. Thank you. 0.23. Now, take it away. What happens now, Anthony?
So the volume has been increased, so the system and the pressure has fallen, so the system would be looking to shift to equilibrium to increase pressure, so they would be wanting to produce more moles of gas, so we should be seeing equilibrium shift to the right.
Good.
And
one tip, Anthony, when you're explaining it in your exams, what are you going to explicitly make sure you mention for pressure? Is there anything?
Le Chatelier's principle.
Yeah, anything else? See, this is what makes the HC challenging to get full marks in, right? It's virtually impossible to get 100 in your HSC Chem exams because you'll always, I hope you don't, but it's just almost virtually impossible to not miss a single point.
Is it collision theory?
No, you don't need to talk about collision.
Right.
You need to mention the number of gas moles on the left-hand side and right-hand side. Always mention that. So you need to say it's always going to shift. It's going to shift in this case to the right-hand side to favor 4 moles of gas versus the left-hand side, bracket 2 moles of gas. Very small thing, and I know you all know. You can do quick maths, but you should always have it in your answer. Good. So go back to your answer, Anthony. You said it's going to shift to the right. So
Yes.
we're going to increase our products, which in this case is ethyne and hydrogen. Now, I want you all to comment down how much you are increasing your ethyne and hydrogen by. I want to see how you guys all go with this. Give me a number, comment it down. I want to see what you're decreasing your hydrogen and ethyne by. So it's jumped from, did we say your ethyne's at 0.23? Yeah, good. I'll just write what everything is. So your, okay, I don't see any comments yet. So I'm just going to start picking on people. Taha, what did you increase your ethyne concentration by?
I would assume you just increase it by 0.06.
Okay, what number are you trying to stay under?
0.46.
Yeah, so you don't want to return back to full. So this is testing this principle here, right? If you increase the concentration back to its original levels, you'll lose a mark. So you always need to show, you basically need to find the smallest unit change for one of the molecules, and you need to be less than that when you return back to equilibrium. So that's my tip to you, right? So I would focus straight on your ethyne, and since it's at 0.23, you can increase it by how much ever you want, but it should never ever return back to 0.46, and everything else should follow the ratio, right? So let's say we increase that up to, let's keep it, let's do 0.4, right? And it returned to equilibrium at 90 minutes, so you want to show it plateauing only at 90 minutes. So you get to 90, and you'll show this. Good. So let's say we've increased it to 0.4, right? So now 1 unit change represents 0.17 moles per liter change in concentration. So how much would your hydrogen increase by, Anthony?
Should go up by 0.51.
Yeah, so 3 times this. Yeah, very good. So whatever that is, it goes up to 0.51. So what's the final concentration now for hydrogen? Someone calculate and tell me.
1.2.
1.2. Good. Make it increase right there. Good. So it should look like this. Good. And what about your hydrogen, Arik? Same principle. Sorry, not your hydrogen, your methane. Does that increase?
That would go down by 0.34.
Good. 0.34. Yes, good. And so what's the final level now? So was it at 0.92, I'm guessing? So if it decreases by 0.34, is that 0.58? Is that right, everyone?
0.6.
0.6? Okay. Good. It decreases down here, and then it's going to plateau. That's it. And that's how you do this question. So this is probably the most challenging concentration time graph you can get, which is not that challenging. If you all notice that, if you remember these 3 points, you'll be fine. There's always a partial change in concentration or counteraction. You always follow the Le Chatelier's principle for the counteraction phase, and you always need to follow the stoichiometric ratio. That's it. Any questions so far, everyone? No? So here I just did the question, but I picked another change. But it's the same thing. I used a partial change in concentration and showed that to you. Good. Good job. So your graph should look something like this. Do we have any questions at all? Are you all confident with concentration time graphs and equilibrium time graphs? Good. Then we have finished that concept. We're going to go straight to some KSP questions. Right. I guess before I jump you into KSP questions, these are the main type of KSP calculation questions you will get, which is question 1, going from KSP to your ion concentrations. And you all know that's quite easy because when you have KSP, you have the formula for the product of the molar concentrations, right? Looking here, you have KSP, you can always find B and C's concentration. What about if we're trying to convert KSP to solubility in grams per liter? What's your plan of attack? So, Arik, what are the steps here?
To find solubility.
Yep, in grams per liter. So you're at KSP. What do you need to do to get to grams per liter?
You would have to find your concentration of your solid. So
That's it. Yeah, so you literally just find concentration of not your solid, your ions, right? Because solubility,
your ions, you do stoichiometric ratio to find out your solid, and then because you would have to convert from moles to grams. If you do, like, for instance, like barium sulfate, you would have to use the mole amounts of barium sulfate.
yeah.
Yeah.
So if you're trying to find the solubility, yeah, you find your concentration of your ions and your actual solid. So in this case, if it's AB,
Yeah.
because what this formula tells you, everyone, so if AB forms A plus B, this is the amount of AB that dissolved whenever you calculate its concentration. So that's what you'll be calculating in moles per liter, and you'll convert moles to grams. Very good. What about determining whether a system is at equilibrium? Or let me word this better. When they give you the KSP for a salt, Taha, what is that assuming? What state is that salt solution in? What can we say?
Saturated.
Very good, it's saturated. So if KIP is equal to KSP, we know that the solution is at equilibrium, it's saturated. If KIP is less than KSP, it's not saturated. And which reaction is being favored, Miller?
The forward reaction.
Yeah, and if KIP is greater, you want to always get to KSP, so reverse is favored. Very good. And we'll finally finish off pretty much this module with a common ion effect question, because everything else in this module, I'm quite certain that you can do fine.
Oh wait, so could we do a precipitation reaction to find out if it, like,
Yeah, sure.
precipitate is reached or not? Yeah.
Like this?
Oh yeah, basically.
Okay, so the aim of this game is speed, right? I'm sure you can all do this question, but I want you to answer it as fast as you can. I'll give you about a minute, and be ready to answer my calculation numbers. Good. These questions, once you get the template, it's robotic. You could teach a year 6 kid to do this if you just gave them the steps in the calculator. All right, what we'll do is we're nearing an hour. I might give you a 5-minute break after the next question. Okay. Raise your hand once you've got the answer to this as well. So go as fast as you can. Good. That's very fast. Good job. All right, let's jump right into it. So, Ta, what's the first thing we do?
Identify the KSP for the salt that will form.
Sure. Okay. So what is the KSP for the salt, which is barium sulfate? Take it away, Ta. What's the number?
1.1 times 10 to the negative 10.
Good, right? Now, the first thing you always do is write your equation, right? So in this case, kind of 2 equations we can write, but there is the barium nitrate combining with your sodium sulfate to form your barium sulfate and your sodium nitrate. Well, is this balanced?
No, you need a 2 in front of the.
Good, right. Okay, right. So we've got our reaction here. So straight away, Milith, when you see a question like this where you've been given data about both reagents, what kind of question is it?
You just find the concentration of each to get Q, and then you compare Q to K.
Yeah, good. So yeah, so basically, whenever you've got the data about both reagents, you should all be thinking about limiting excess reagent questions first, right? So that's what I was kind of cueing you all into. In this question, it doesn't matter, and I'll show you why, but usually in a question where you're given data about both reagents, limiting excess reagent is the first thing that should come to your mind, okay? Good. All right, so we've got a V, we've got a C, we've got a V and a C. What do we do, Shashanth, with these values?
You find the moles.
Good, right? So tell me, Shashanth, what is the number of moles of Barium nitrate.
So barium nitrate was 0.0051. And
Store that as A. And what is that also equal to, Shashanth? Which ion do we care about?
that's also equal to barium sulfate.
Yeah, I would say not quite, unless you know that's a little.
And also sodium sulfate as well.
I would just say it's equal to barium, right? That's what I was thinking about. The ion we care about is barium and barium sulfate, right? So in barium nitrate, we care about the barium because that barium is going to go and precipitate with the sulfate. So it'd be good to write that down. Good. And what was your value? Who do we have? ARC for sodium sulfate. What do we get?
Oh, so I just did like C1 V1 equals C2 V2. I just found the concentrations of like each like barium and sulfate.
C1 V1 equals C2 V2. What did you use? What did you use as V2?
My V2 was 0.073.
Yeah, look, that works. That also works. So what he's saying is as a dilution question. Sure, that also works out. Who did it this way? And who got a number of? What did you all get as your number of moles?
0.0046.
0046. Good. We'll store that as B. And Anthony, which ion is this also equal to? Number of
The
moles.
sulfate ion.
Good. That's all we care about, right? Good. Now we should find the new concentrations of barium and sulfate because they're in a beaker and we've added 2 volumes. So the final volume is, as Arik pointed out, 0.73. So we're just going to divide these and get the new concentration of barium and the new concentration of the sulfate, right? So you're going to get A divided by 0.73, B, you're going to divide it by 0.73. I'm not going to ask you for your answer to this. Whatever you got, you should have stored that. And you literally sub that into your KSP equation, right? So this is where you should write the other equation too. So BaSO4 gives you Ba2 plus and SO4 2 minus. Then all you have to do now is A divided by 0.73 times B divided by 0.73. What do we get, Taha? What's your final answer for your... This shouldn't be called ASP, it should just be called QIP, or your ionic product. What do you get?
I accidentally cleared my calculator, so I don't have it.
So shouldn't it be divided by 0.073?
Yes, so not be yes. Apologies. So what I've done is a big silly mistake where I didn't add it up. But good. So I would have written 73 times 10 to the power negative 3 because I always do it in scientific notation. Good. You're completely right. 0.073, 0.073. What do we get as our answer?
0.044.
Did everyone get this?
Yeah.
Yeah.
Good, which is bigger than KSP. I've never seen a KSP that big. So therefore, what would you write next? Shashanth?
So since it's less than, I mean, since it's bigger than KSP, that means
It's
you'd favor the
0.004, not
Yeah, it's 4.4 times 10 negative 3 essentially.
extra 0.
Okay, sure. Okay. Double check your calculation work, Ian. Good. All right, so what do we write next? That's my next question.
So since it's bigger, it'd favor the reverse reaction and that'd form precipitate.
Okay, good. Reverse reaction favored. I'm looking for one more thing.
Precipitate formed.
Yeah, we've said that. What else? One more thing.
Saturated.
Well, of course it's saturated. It's super saturated, right? Saturation is that point where you either form a mild precipitate, faint precipitate they'll give you in questions, or there's no precipitate. It's super saturated when you form a precipitate. So you want to identify that. Good. And that's 4 marks. So you would have rounded that off to the correct sig fig. So that would be to 1 sig fig. So you would have written 0.004 rounded off to 1 sig fig. But good job. All right, Arik, did that answer your question about doing those? It's not too hard. Right? Let's go to...
It can just get annoying when you have to just do like the stoichiometric ratios, but like, yeah, that's fine either way.
We're going to do this question now, and then you will be offered your break. So the question here is calculate mass of the lead nitrate. 2 moles. It should be 3, around 3. Okay, do this question again. I'm not going to say anything, and raise your hand once you get an answer. After this, we'll have a common ion effect question, and I think otherwise, unless you all have any specific question requests, the rest of mod 5 is quite straightforward. It might be worth jumping to mod 6 after the break. Okay, so hopefully most of us would have solved this by now. So let's jump into it. Okay, so Anthony, tell me the steps. What do we do here?
Firstly, I just wrote out the equation for lead chloride, which is PbCl2 produces lead 2 plus 2 Cl minus.
Yep, good. Yep, and then
Then I worked out the concentration of chloride ions within the solution, which is given by 0.1 moles times the 0.1 volume, and then you divide that by the new volume of the solution, which is 0.35 liters. And I stored that value.
Good. Okay, so first thing you did was you found the initial concentration of potassium chloride, which is equal to the concentration of chloride ions, which is equal to N on V, which is 0.1 divided by 0.1. Isn't that 1?
Wait. 0.1. Isn't it 0.1 times 0.1?
This is an N value. This is a V value. C is equal to N divided by V.
Oh no,
What
no,
we-
I found N first, and then I divided it by the new volume, because you've added 100 mils to a 250 mil solution.
Right, okay, sure. So you fix the number of moles and you divide it by the total volume. Is that right?
Yes. Yeah.
Okay, all right, that makes sense. That also works. Good. All right, so you've done that and you've added 250 plus 100 times 10 to the power negative 3. Good. So what did you get then?
0.02857.
0.02857. And that would be your final concentration of chloride ions in the
Yes.
solution. Good. All right, so you've got the final concentration already. Good. And Ayan, what did you do next?
That's all I got up to.
Okay, good. Keep going. And Shashanth, what did you do next?
That's what I got up to as well.
Okay. Milip, what's the next step?
I did it slightly differently.
You can still, yeah, but you can still
But, yeah.
work this out from this step.
From
Take
this stage, with that number, I would just divide the KSP by that after squaring it.
Good. So you understand that whenever there's a very faint precipitate formed, we're assuming it's a saturated solution, so we can operate with KSP, right? That's the one assumption you need to work with KSP, everyone, right? That it's saturated or you've been told there's a faint precipitate. So good. So you know the KSP value, and what is it, Milith, from your data sheet?
1.7 times 10 to the negative 5.
Right, and that's equal to the concentration of Pb2 plus times Cl minus concentration squared, right? And that's equal to 1.7 times 10 to the power negative 5. So what he'll do next is find the concentration of Pb2 plus ions. So what it can do is 1.7 times 10 to the power negative 5. And let's say we stored this concentration of chloride ions. We'll store it as C. Right, so we're going to divide this value by C squared. What do we get as our concentration of lead ions in solution, everyone?
Something like 0.0208-ish.
0.208.
0.0208, yeah.
Is it 0.0208?
Yes.
Okay, we'll store that then as, we'll say A. Good. And going back to you,
Wait,
Taha?
so
Hmm.
the KSP be equal to, since chloride has a coefficient of 2, then wouldn't it be equal to 4x cubed?
Wouldn't it be equal to 4, as in 4C cubed in this case, since I stored it as C?
Yeah, like to find.
See, it would, Taha, if you had that scenario where PbCl2 is forming Pb2 plus and Cl 2Cl minus, and it would have been the case, Taha, if we added PbCl2 to a beaker of water and it dissociated to form Cl minus, etc. Right? But in this case, do you agree there was no PbCl2 directly added? There was some KCl and there was some PbNO3. Right? So in this case, when PbCl2 was added, then you can say, well, if the concentration of PbCl2 is A, then chloride ions is 2A. And so when you put in the formula, I understand you're going to say you get 2A and you have to square it, and that will put you in 4A squared. That's what you're talking about, right?
Yeah.
But we haven't been given a value for the concentration of PbCl2 that was formed. All we know is there was some potassium chloride, and that gave off chloride ions. So we're literally going to get that chloride ion concentration, sub it straight in, and just square it.
Oh, okay.
Yeah? You see
Yeah.
why it's different?
Yeah.
Okay, so your approach now is, what we're at now. So we've got the lead concentration. What can we do now, Anthony?
Then you can just multiply that by the volume of the solution to get the number of moles, and then multiply that by the molar mass to get
Good. Number of moles of Pb2 plus is equal to Cv, and we know that concentration is A. So what we stored it as, and our V value is, remember, it's a whole beaker, which has 250 ml and 100 ml. So that's 350 times 10 to the power negative 3. And whatever you get there, we'll store it as B, and then you're just going to use number of moles equal to mass times molar mass. So mass. Now, small tip, whenever you're writing equations, please write the normal. If you work really quickly in your HC exams, you might make a silly mistake there, and it'll be very hard for you to pick that up when you're double checking. So just always have fail safes, so you're literally perfect. The goal for the HSC should be to get as close to 100 as possible, if not 100. Good. So you're just going to do number of moles times molar mass, and what do we get? What's our final answer for the mass of lead nitrate?
I got 2.414 grams.
2.414 grams. How many sig figs?
There should be 2, so 2.4 grams.
You sure it's 2 sig figs?
Oh, wait.
100.1.
Wait, isn't it 2?
How many sig figs is 0.1, everyone?
1.
So there's any number after a decimal point is significant. So 0.10 would be 2 sig figs. In maths, I know 100 is 1, 2, or 3, depending on what you rounded it off from. But in chem, you assume worst case. You assume that's 1.
Okay.
Good. So this would round off to 2 grams. 1 sig fig. Did everyone get 2 grams?
I was getting 1.5 ish.
Yeah. Shashanth, what did you get?
I got 2.4 times 10 to the power negative 5. Maybe it's just some significant ding error.
Can't get 3 different answers. Who's going to help the consensus?
I think it's probably 2.4. I might have just had a different power in between.
Serene, what did you get?
Yeah, 2.4 times our
Good. And
I think Milth got 1.5 because he times the molar mass of lead itself instead of.
Mila, did you use molar mass of just lead or molar mass of lead nitrate? Because the question is calculate the mass of lead nitrate.
Oh, okay, yeah. I did molar mass of lead. Yeah, I did mass of lead rather.
Every time you make a silly mistake, you should get a red pen out, circle it, and highlight it so you don't make it again. Good. So just make sure you use the molar mass of the entire compound. Good. I'm going a bit fast, everyone, but that's because I know that you all know how to do the key things here. I want to focus more on challenging you. And for mod 5, there's not too much that is challenging, to be honest. It's probably the easiest module. Did you have any hard, so you mentioned you had that weird enzymes question for chem. Was there any of the mod 5 questions that were hard at all, or a bit of a tangent, or was every other mod 5 question in your trials just straightforward? Like,
I think there was one KSP question. I'm just trying to remember exactly what it said, but it gave the situation as a faint precipitate forming, and they gave a bunch of values. I think one of them was close to KSP, but it was slightly under, and the other one was considerably above KSP, but would definitely form a precipitate.
And what was the question? Was it to do with whether a precipitate forms?
I think it was to do with concentration. So you had to backtrack from the. I'm not sure, Taha. Can you remember exactly?
Yeah,
what
it was like what mass of this compound or concentration or moles would give a faint precipitate. Would produce a precipitate.
Then you just have to go to the K value. Oh, okay. So that's slightly more conceptual, right? Now this is a very important thing. At a temperature, if your K value is below KSP, you should not form a precipitate, right? The other K value, was it much higher than KSP?
It was not much higher, but it was considerably higher.
It's a bit hard to see that the numbers are so small that what seems considerably higher could be slightly higher, for example, based on, because it's all scientific notation. I would have gone with the option, well, I haven't seen the numbers, but you would go with the option in which your Q value is greater than K. Because if it's less, you don't form a precipitate at all. When you're at K, you still will either not form a precipitate or you form a slight precipitate. Okay, and that's what they call a faint precipitate. It varies, but you would not pick a value less than K if they told you a precipitate forms. Good. All right, this is literally the same question, but I guess just to, not to do it, but ppm, what's the alternate unit for ppm, Ayan?
Milligrams per kilogram.
Good. Or in solution, it's milligrams per liter, because water has a fixed density of 1 cubic centimeter, or 1 gram per ml. Very good. All right, I'll put you straight into a KSP question. We can have a break after this. So the degree of calcium sulfate precipitate that'll form in do this. No, we'll do this one. There you go. Don't worry about the qualitative, just quantitatively do it. And again, work on your speed for this question. This will probably be the final question type that. I guess the hardest part, everyone, with common ion effect questions is they'll never tell you it's a common ion effect question. So make sure whenever they talk about adding a salt to an existing salt solution, you look for a common ion. They can represent this through graphs as well and ask you to explain the graph and calculate from the graph. So that's the only variation you can have. Good. Aim to do it in about 2 minutes. So raise your hand once you've done this question, and then if you finish early, you can go take a break as well. Okay, good. So most of us have solved this. So what we'll do is I will give you about 5 minutes to take a break, and we'll recap at about, what's the time now? 3:40? 3:45. Okay, so stretch, get some water. And if you have any questions as well, I think what you can also do, everyone, is try finding any Mod 5 questions maybe that you wanted to flag earlier, or even go back to our posts where you all posted questions pre your trials. And if there's any specific questions you'd like me to go over again, this is your final chance for Mod 5.
Wait, so is today just specifically on Mod 5?
Yeah, it was meant to be mainly Mod 5, but I thought we could speed it up, and I guess the next hour we'll do Mod 6.
Okay.
Okay, good. All right, we'll recap at 45. See you all then. All right, is everyone back? So just lower your hand if you are back. And feel free to turn your camera on. It's completely optional, because I know with the whole online situation, sometimes it can feel a bit exhausting to have your camera on the whole time, so that's all fine. Okay, good. Did anyone get up to anything interesting outside of their HSC trials or after the HSC trials? Anyone read any books?
I started biking again.
You started what?
Biking.
Biking. Nice. Nice. That's good. Good physical activity, and it gets you around, and some vitamin D. Good. Anyone else? I got a massive 88 key piano and I didn't get a stand for it, so it's just sitting on the floor, so I can't play it. But I'm excited to just go on YouTube and self-teach because I know quite a few students. So this is the weird thing when you speak to a lot of James Root students. I remember when I was in my first year of medicine and I was just asking them what they were all doing in the HSC. They're all like learning instruments and violin and doing all sorts of cool stuff outside, and that made me feel a bit inadequate. So I guess now I've started to try learning an instrument. So I taught myself for a release and forgotten it all in a couple of months. So I'm going to relearn. Right, let's jump into things. So, Taha, how do you break this one down?
So you basically have to compare the values with the KSP to see which is more soluble.
Right, my question to you is, right, you've got lead iodide and you've got it in a potassium iodide solution and in water. Those are your two case scenarios, right? What are you going to compare? Are you going to be comparing the concentration of lead ions or iodide ions between these two scenarios? Anthony, what are you going to compare?
The potassium ions.
Okay, you'll compare
Oh wait.
potassium ions? There's
No,
no
sorry,
potassium.
lead. I mean, yeah.
Lead. Good. Yeah, you'd compare lead. The reason being, everyone, what you're trying to show is that in water, the concentration of lead ions is a particular amount, and in potassium iodide, there are slightly less lead ions. That is what you want to show to prove the common ion effect. If you're looking at iodide ions, you're going to find the concentration of iodide ions is equal to X. And here you're going to find the concentration of iodide is going to be slightly less than X, but you're going to have 0.1 moles per liter added to it from the potassium iodide. So you're not going to be able to show that the iodide concentration has decreased. In fact, it'll look like it's increased because of this common ion amount here. So always remember, you're trying to prove the other ion has decreased, not the ion that's actually common among the two solutions. That's what the common ion effect is. The addition of a common ion to a insoluble salt like lead iodide will decrease its solubility and even make the other ion's soluble concentration decline. Good. So let's jump straight into it. So water, I know you can all do that. So with water, we get the KSP. And what is the KSP for lead? Ayan, what did you get for KSP of lead?
9.8 times 10 to the power of -9.
All right, good. And you'd also write the equation, right? So lead iodide forms lead 2 plus and 2 iodide minus. Good. So, Ayan, take it away. What do you do next?
I'm not sure.
Okay, what I would do is I would let the concentration of lead iodide be X, right? Because, Ayan, remember, what you're trying to do is you're trying to show that the concentration of lead ions is going to be less in a common ion solution versus water, right? So the goal is find concentration of lead in each scenario. So we want to find this concentration. Do you agree?
Yeah.
Before that, I'm going to assume the concentration. This is what Taha was mentioning earlier. We're going to assume the concentration of PbI2 is X, and that would make the concentration of Pb2 plus also X because of the 1-to-1 ratio, and the iodide ion would be 2X. And then we just sub that in. Well, what is KSP? KSP is lead ion concentration times iodide ion concentration squared because of the 2. And that's going to be equal to X times 2X squared. And that's how you know you're along on the right track, when the number inside and outside the bracket is equal, right? Good. So can someone tell me what X is equal to and what that means? So yeah, anyone?
I got 1.34 times 10 to the negative 3.
Yep,
Good.
same.
And what is X, Milith? What does it
That
mean
is your molar solubility. in-
of lead, right? So we're just going to write solubility of lead is that value here. And you can even say the concentration of lead iodide that actually dissolved is equal to that same value as well, because it's a 1-to-1 ratio, right? So you can feel free to do that as well. Good. So you've got that value here. Now let's do it with your potassium iodide solution. So I will get Shashanth, take it away. What do I do now?
So I drew an ice table, and
One
pretty-
thing, I'm just gonna pause you right there for 1 sec, Shashank. Now, for an ice table, the way I know when to do an ice table is I apply whenever I need to find K, I should be thinking ice table. Whenever I need to find pH and I'm given K or I'm given pK, I want to consider doing an ice table, right? With your salt and solution equilibria questions, you can do an ice table, but it's not really necessary. You won't really need to do it. And I'll explain to you why that is, right? So did anyone do this without like drawing up a ice table formally?
I did it for ice table as well.
Yeah, look, it's fine. I'm technically going to be doing it with an ice table, but I'm just going to be doing it a little bit faster, right? What I want to write here is in potassium iodide solution, I'm going to follow the exact same steps. PbI2 gives me Pb2 plus and 2 iodide, right? Okay, if you did an ice table, that's fine, completely correct, but I'm just showing you an alternate way to do things, which is a little bit faster. Right, we're going to do the same thing, right? We're going to let the concentration of PbI2 that dissolved now, we'll let it equal to y because we know and we're trying to show that y is a little less than x. Everyone agree? So now we're going to say the concentration of lead ions is also equal to y. This is all equilibrium concentrations. And we're going to say the concentration of iodide ions is now equal to 2y. But do you all agree we also have a concentration of potassium iodide that is 0.1? And that's going to ionize and release an equal concentration of iodide ions. So we have to add 0.1 to the 2y. So the only difference here is you have to add the concentration of that common ion in. Everyone with me? Right? And then I'm going to apply the exact same steps, right? So I'm going to write KSP is equal to y. Well, I'm not going to jump steps, but it's going to be Pb2 plus times I minus squared. And that's going to be equal to y times 2y plus 0.1 squared. Now, Anthony, do I ever have to do quadratics in chemistry?
Sometimes.
Yeah, I would say no. I don't think standard students, I would say actually it's an absolute no. Whenever you have to do quadratics, you can always assume that the value is close enough to 0. In trials, sure, it's good to do quadratics. I would still do it in the HSC since you know quadratics personally, but you don't need to. So in this case, what we can do is just for this internal y in the brackets to make this a linear equation, we can assume it's so small it's close to 0, right? And so that's just going to be y times 0.1 squared. So y is equal to 9.8 times 10 to the power negative 9 divided by 0.1 squared. Good. What do we get as our y value?
9.8 times 10 to the negative 7.
Good. And Millet, can you compare that to this value here? Less or more, and by big magnitude or small magnitude?
Less by, well, it's not really a big amount, but it is less. I mean, they're both small, but
Yeah, they are both
negative
small,
three.
but I'd say relatively it's magnitudes of difference given that -3 and -7. But you're right, both are absolute small numbers, but relatively this is, you know, thousands off the original concentration, right? Good. So that's your final answer, and all you have to identify is this is less than the concentration of lead, or what I write, lead nitrate, it's lead iodide. So this is less than the concentration of lead iodide in water. And right, therefore, common ion effect.
So for qualitatively, do we just name drop the common ion effect, or do we have to somehow explain like how, like how it happens?
Yeah, you have to explain how it happens. So who wants to give that a go? Verbally, Taha, give it a go.
When there is more iodide in the solution, then the equilibrium will want to shift to the left and produce more precipitate. So therefore, the solubility of lead will decrease.
Good, you got the gist there. Anyone, what would you all add? Because remember, HSC
Definitely.
looks for specific things. Arik?
I mean, I'd say like an addition of iodide ions, which is a common ion, will result in the equilibrium to shift to the left by Le Chatelier's principle.
Good. So the first thing I want to hear is it's the mechanism of the common ion effect is Le Chatelier's principle. The common ion effect is just a fancy application of Le Chatelier's principle in salt solutions. So you must mention Le Chatelier's principle or you'd lose a mark. Good. The other thing I'd mention is clarify what the stimulus is. The addition of a common ion increases the concentration, in this case of iodide ions, in the potassium iodide solution, right? And since potassium iodide is an insoluble salt, it forms an equilibrium, and then you can go from there.
Wait, do we
Good.
say that the precipitation results in the solubility decreasing?
You would say that so the way I would structure this question is I would identify it's through Le Chatelier's principle, and I'd follow the exact 3 questions you always ask yourself. So the equilibrium shifts to the left, thus increasing the amount of precipitate formed and decreasing solubility. That's just the final thing I would say. Yeah. Good. Any
So
questions about common ion effect?
Oh.
Yeah.
I sent the enzyme question in the chat.
Oh, interesting. Okay, I'll have a read of it while I give you another question, just so we can save ourselves some time. So I think that's everything for Mod 5, everyone. Does anyone have any questions? You're going to get access to all of the slides, so you can do as many of the questions as you want. There is a whole question about indigenous detoxification of food, right? So the cycad, and this is just a little sample answer you can quite literally copy paste. If you've forgotten this, I guess you can quite literally have a look here and you can understand it. The solubility of cycacin is very high. It's about 56 grams per mole. And thus, when you put it in a basket with running water, you can leach that cycacin toxin from the cycad fruit. And then they do a couple of other things, such as burying it underground, and that allows enzymes to catalyze reactions to decompose the toxin as well. And then there's heating as well to denature the toxin. Good. So that's everything here. So you just need to know the properties, the chemical properties that allow those detoxification processes to occur. So high solubility is one. Another one is fermentation as well. Good.
Wait, so would you want me to send my like whole trial paper to you?
Yeah, that'd be good. If any of you have your entire trial paper, please do send it across. I would want to definitely see the questions asked this year to see how you all went, and if there's anything that I could reinforce or clarify for you. Good. And also, please make sure all of you message me how you went in your trials. Okay, I don't care if it's good, bad, mediocre. I want to know how you went, so I can kind of see how much support you need and whether you're actually good, and any questions that or clarification points that you might have. Okay, because I want you to leave my teaching and mentoring being fully confident and ready to sit your HSC exams. Okay, good. All right, so you can do the rest of those questions in your own time. Start with Mod 6. Okay. Mod 6, I would say, the only things I'd like you to focus on is titration. Very likely you'll get some kind of weird titration question you may not have seen before. It might be looking at titration of oxygen levels. That's what we call Winkler's titration. That's been asked before. You may get some titration involving a pH probe, and you have to analyze questions about graphs. That has never been asked before properly. There's been, I think, an MCQ or a short response. So be ready to get a conductometric graph and explain that, etc. With what students find hard, it tends to be your Ka, pK, pH questions. It tends to be your questions about titration methodology. And it tends to be questions about buffers and your curves. So that's what we're going to be focusing on here. I'm probably going to skip historical theories of acids because you just have to literally know the key points, right? What did Arrhenius do? What are the pros and cons? What was Bronsted-Lowry pros and cons? Does anyone have any questions or any other parts of this module that you find challenging that you'd like me to go over?
I find challenging about like the buffer region, like how to explain those stuff. Yeah.
Sure. Right. I think, Arik, what would really help is do you have your buffer region question? If you can take a picture and send that, I can show the entire class how to approach that question.
Yeah. Yeah. I'll just send her like in 3 or 5 minutes. Yeah.
Yeah, sure. Send it whenever. All right. Good. Let's jump straight into things. So some of these questions are from your exam, so we'll skip those. Here's your first question with pH, pK, etc. Let's give this one a quick go. To use this for speed, and in the meantime, I'm going to be going through the question that you've all sent. And the question you all had is a biology question. So it's a year 11 biology question. It's quite interesting. Enzyme substrate graphs. We'll go through that, and I think we can go through that next, especially given that it's to do with equilibrium and what we just went through. I think the issue with that question is it's pretty vague. I think you'll understand, like I know you will understand what's going on there, but then like how do you get 4 marks? That would, I guess, be the main challenge point. Okay, we'll go through that. Okay. Now, a yarn, yeah, that's also fine. Chem paper, marking guidelines. Oh, they've broken things down using Excel. Okay, can you guys raise your hand once you've done this question? I think you all would have done it, right? Finished? Good, just so I know. And Eric, what question from your exam? I'm fine going through Mod 8 as well, if we have time. So
Yeah.
what?
It was just question 24, say, because if you look at the average, like everyone screwed up that question. It was like that bad. It was about location, like where would you do your like ammonium, like where would you store an ammonium nitrate and all that.
These questions, everyone, is quite, your exams are going to be very heavily based on things like this.
Yeah, because if you look at the marking criteria, their response is like so broad. Like I would never like expect some stuff from their answer.
I'll have a look at that, but for now, let's quickly do this one. Okay, so Taha, what's the first thing that comes to your mind with this question, with its approach?
Well, I can see that there is Ka, and my goal, since it's to find pH, I want to find the concentration of H, which I can do using Ka.
Good, right? And one thing you should consider always is to do a rice table, right? So it's my artistic impression. But don't forget, whenever you have a K question, especially with pH involved as well, always consider whether you need to do a rice table. In this case, you may not need to because it'll be pretty fast, right? So take it away, Shashanth. What do we do?
See, right at the equation, and since it's monoprotic, well, I drew the ice table for this, but
That's fine. Yeah.
so I guess the final equation you get is x squared divided by 0.1 minus x, which you would just approximate to 0.1, equals 1.75 times 10 to the power negative 5, which is just the Ka value.
Good, right? That's a key point. So you definitely can do a rice table, and I would encourage you to do one, right? So the way you know you need to do a rice table is pH is always an equilibrium concentration, right? So equilibrium concentration of hydrogen ions determines the pH. This value here is an initial concentration. If you have an equilibrium concentration and an initial concentration, you must do the ice table, right? But some of you might overlook it in the terms that you know to do it and you speed through it. So you can quite literally say, well, we know that initially it was 0.1 and it would have decreased by x, so obviously it's 0.1 minus x. We don't care about the water, and we know that these concentrations are equal and they're both going to increase by x. So you kind of don't need to do an ice table if you've seen enough of these questions. And you can say what Shashanth mentioned, which is k is x squared divided by 0.1 minus x, and that's 1.75 times 10 to the power negative 5. And you solve for x. Shashanth, what can we assume about this x value at the denominator?
That it'd be close to 0.
Good. So you just write x squared is equal to 1.1 times 1.75 times 10 to the power negative 5. What do we get as x? And actually, don't worry about the x. Tell me what the pH is, everyone.
2.9.
Is that your final answer?
Yes.
Good. Yeah. So your pH is rounded off to the decimal places of the sig figs in your answer. So your question has 1 sig fig, so your pH value will be to 1 decimal place, right? So you round it to the lowest number of sig figs, but in decimal places for your answer for pH. So yeah, you just write 2.9. And you don't have to write units. Don't worry about that. Just write 1 dp. Good. Pretty easy question. Let's move on to the next. Actually, well, let's do Millet's question now. So I'll let you all think about this, and especially the Holston students, you can have a second look at it now. It's in the comment section, so I will just go back to that and put it up for you. But what does it mean by glacial acetic acid? Very good. It does mean anhydrous. Good.
This is another tough question, I think.
Oh, buffer question.
Yeah.
Sure. We'll do that next. Sure. All right, everyone, have a look at this question. I'm going to be looking at the buffer question while you're looking at this one, just so I can speed up and guide you through it. So please make sure you're looking at the enzyme substrate question. I'm just flicking through this to read it all. And raise your hand once you've got a plan for the 4 points you would mention. We're looking at this. H. This is a bit of a, funky question. Hydrochloric acid reacts with methanoid ions. Okay, we'll need to do it as we go through this one. This is more of a calculation one. All right. Good. All right, so let's have a look at this. Now, hopefully you've had a look at all of this paragraphs of enzymes, half of which are not important to you, except for these equations right here. And I guess the key point here is, I'll include the question so we don't brush over it. The key point is this is a fast reaction, almost immediate, and this is a slower reaction. Okay, good. So we can say fast or immediate and assume it's always in equilibrium from time equals 0. Equilibrium from t equals 0. Good. Now, using equilibrium principles, explain the shape of the graph above. Now, for explaining the shape of the graph, you need to explain the initial increase, the decrease, and why it plateaus. Those are the key 3 changes in the graph. And you need to refer to rate of reaction, right? Now, what determines the rate of reaction? What theory are you going to be using, Anthony?
Collision theory.
Yeah, right. So given it's a 4-mark question, to be safe, I'd probably define collision theory and how it affects reaction rates. Or if you're really good, you don't have to define it. You can actually define it in your explanation of collision theory. And we'll get to that, right? So let's assume that's not even given a mark. So we'll assume we're just going to do that before we answer the question. Now, what would be a helpful tip for all of you? What would you all do? Those of you who've done this question, there's one small thing you can do to kind of help yourself out a ton. Any ideas on what you can do regarding the equations, to be specific? Anything you can do? Well, do you all realize these are interrelated equations? Right? Equation 2 affects equation 1. So it might help for you to write it as one entire equation as well. So you can clearly see how a change in concentration of one substance is going to affect the other. So that ES we assume is immediately formed, and then it will break down to form E and P. Does that make sense to everyone? And we're assuming from time equals 0, we form an equilibrium with some ES, some E and S, and then the reaction begins to proceed to form E and P. Now, logically, everyone, we're looking at rate of reaction, which is for reaction number 2, right? This is for reaction number 2, this one right here. Why is reaction rate initially high? Why is there a high reaction rate? Taha, explain that to me.
So since the first reaction is faster, there is a higher concentration of the substrate being produced. And since that substrate is used as a reactant in the second reaction, then it favors the forward reaction to produce more product. So initially, there's like a fast rate of formation of the
Okay,
product.
everyone, what has he not referred to that I'd like you to refer to? It's a good answer, Taha, but I'm just nitpicking to be very picky.
Collision
Miller?
theory.
Yeah, collision theory, right? Initially, since we're assuming, so I don't like talking about substrate, product, this is chemistry here. So just call it ES or P, right? To make your life easy. Initially, from time equals 0, E and S immediately combine to form ES. Do you all agree? So we're assuming pretty much from time equals 0, there is a ready available concentration of ES, and it's at its highest, right? So molecules of E and S can collide, engage in successful reactions to form your product, which is P. And that's what's being measured as your rate of reaction. The rate of reaction is just the rate of formation of P, right? So we can say at time equals 0, given that the first reaction occurs almost immediately, we have the highest concentration of ES. Thus, we'll have a high number of particle collisions of ES, so your enzyme and substrate complex, and this will result in a high rate of formation of P due to increased successful collisions.
Wait,
right?
so
Yeah.
would it be okay? For my first point, what I did was I talked about the change in equilibrium of an increase in S concentration, and then according to LCP, it favors the production of ES, which then, according to collision theory, increases the production of the product. So I talked about LCP for the first one because they used that equilibrium error, and then I talked about collision theory for the second one.
That is completely fine. What I'm looking at here is where it says that S is in an excess above enzyme. The formation of enzyme is
Wait, since it says use equilibrium principles, did they want us to refer to both LCP and collision?
Yes. Yeah, I would refer to both, definitely. I'm just looking for where it says that there's going to be a relative excess of S. Is it cut out from what I've screenshotted?
No, I just assumed it because they we can see in the x-axis is substrate concentration. So if we're adding substrate, then that concentration is increasing. Right?
Yeah, no, definitely. Yeah, so I would say that definitely would also give you a mark, right? So looking at the x-axis too, that as substrate concentration increases, that's referring to how this equilibrium would be affected. For sure. Yeah. I guess, the first thing I would mention would be talking about ES particles colliding to form E and P, and that's why there's a high rate of reaction. And then, Milith, I talk about as you further increase substrate concentration, this is going to, through Le Chatelier's principle, shift the first equilibrium to the right? And that's going to increase the molecules of ES. Good. So that would I would say that'd probably be about 2 marks in itself. So the first mark I would say would be from explaining the initial increase due to collision theory with a second reaction, right? And then you'd also get 1 mark for LCP, and linking that as you increase substrate concentration, you will increase your enzyme substrate complex. You will shift it to the right, and thus have more enzyme substrate complex molecules to react and form E and P. The only thing though is, in reality, given that I do biology, I can tell you that the second reaction will happen very fast. So ES will actually be depleted, even though we're increasing substrate concentration. If everyone's with me, right? Even though we're increasing substrate concentration, this gets depleted very quickly. So the net change is there'll be a decrease in ES, even over an increased substrate concentration. That is why the rate of reaction starts to plateau. Does that make sense, Millet? Because according to you, if enzyme substrate concentration keeps increasing as we increase substrate concentration, well, then this reaction should occur at a faster rate because we have a greater concentration.
But since the second reaction, wait, are you just talking about like natural in real life instead of for the question?
Yes, but also I'm saying your point is completely correct. But yeah, in real life, the net changes, enzyme substrate concentration will decrease. And that's
Oh.
what causes that plateau. Yeah. Yeah, good. Okay, so how about the next point? What would you mention next? So Anthony?
So we've mentioned the initial state. So you'd say should we talk more about how it begins to plateau as substrate concentration increases, because now you have a relative excess of ES being produced relatively quickly, whilst the second reaction, which takes a relatively longer time, is still slow. So overall, the rate of reaction is going to be slowed down.
Yeah. Anything else that anyone would like to add on?
I talked about, since ES is building up because of the second reaction being slower, at some point the addition of S does not lead to the dissociation. The production of ES, kind of like we have those conductometric curves that plateau out when you keep adding a particular reactant, because equilibrium favors that other side already so much, and that would lead to a plateau of the rate of reaction.
Good, good. It all and depend on how you write it on paper in the end. But I guess the first thing I would say, like I mentioned, is mentioning that initially we have a high reaction rate due to the maximum amount of ES that is present, right? Because we're assuming reaction 1 occurs almost immediately. And then what we can say is, as the reaction proceeds, ES begins to be depleted, right? And that's going to reduce our successful collisions in forming our product. And how's it going to affect this equilibrium here? It's going to shift it in what direction?
Slightly.
Right.
Yeah, so the second point I would mention would be, the point number 2 would be, as we proceed through the reaction, we're going to get a decrease in ES concentration. And we're also going to observe there's going to be an increase in substrate concentration as we're moving along that graph, right? As you can see, the substrate concentration is the x-axis. Both of those things will shift the equilibrium in reaction 1 to the right-hand side. Everyone with me? So then I would mention this is according to LCP. And that's where I'd link in the Chatelier's principle. Good. Right. So although that's all happening, right, although we're shifting to the right, is that going to completely counteract this decrease in ES caused by this reaction here occurring?
No.
No, so I would still mention, however, there is still a net decrease in ES, which results in a decreased number of collisions and decreased successful collisions, as LCP is a partial counteraction. And this leads to a plateau in reaction rate observed in this graph. And the final thing would be, so I'll write that down for you as well. However, it's partial. There's still an overall reduction in ES, which leads to decreased successful collisions and decreased reaction rates. Good. Why did the reaction plateau, everyone? What happens there? Who can tell me why it plateaued?
Because ES was exhausted.
Yeah, ES was exhausted. Enzyme substrate was exhausted. Yeah. Yeah. So if I had to be very specific with this, I would mention that ES proceeds. Let's see, who else has any points? Shashanth? Anything you would mention as to why we're talking about the plateau now, so focus solely there.
I sort of went a bit with like biology in the sense that I said that there'd be because there's a finite number of enzyme substrate complexes, and regardless of how much substrate you add, there won't be any reaction. There won't be that much of an increase in reaction because all the substrates are already taken by the. All the complexes are already taken by the substrates.
Millet, the reason I would say that ES, you can't say ES completely disappears, is because you know the E formed here is reused, goes back to the E here. And so you'll always have enzyme substrate complexes. Does that make sense? looking at that reaction there. And so I would say what's actually happened is all of the E is occupied as ES. Everyone with me? So that's technically means there is E has depleted. There is no available E to react and form more ES. Does that make sense to everyone? Right? So I would say it as if the first reaction, that equilibrium reaction, has been completely depleted. Okay? And what that does is there is a fixed amount of ES, right? Its concentration will not change because there's no more E to react to form ES. Do you all agree? There is a fixed amount of ES. Fixed number of particles means a fixed number of collisions, which means a constant reaction rate. And that's what you observe there. So my final point would be for the plateau, I would mention there has been a depletion of available E. And that's because according to chemistry terms, your S has become your excess reagent, and your E is now your limiting reagent. Okay, you can state it as that. And what that does is therefore the equilibrium will dissipate right here, dissipate, and concentration of ES becomes constant. That's constant collisions. That will give you a constant reaction rate. Now, this is just my rough sketch to this question. These are one of those questions where you'd want to finish the exam early and double check, think of your syllabus and think, well, is there any other points that I'd like to mention? Right? Thinking here, not at the moment. But I think this is something that you would want to go back to and double check for your explanations. But did that make sense to all of you? Is there anything else? Did anyone mention anything slightly different that they just want to clarify and see whether it makes sense or is right? Anthony?
I think I basically made the same point at the end about how the enzymes get like depleted by the reaction, so the rate of reaction slows overall. But yeah, I guess I can't remember my exact answer. So
Okay. Yeah. Good. Yeah. I would probably move on to the next question after writing this, and then I'd come back and double check it and spend a good 5-10 minutes thinking about any other points from the syllabus I'd like to add. Your HSC will not be like this. This is very much a bio question. This is probably because your teachers had to find some way of making very specific niche questions for you. This is not how a HSC question would be. It'd be much more chemistry, and it would be much more analysis, table and graph rather than paragraphs of concepts. Okay, good. Any questions so far? I wouldn't worry about this popping up in your HSC. What I would be concerned about, everyone, is whether you can explain the Shadley's principle and temperature changes according to reaction rate. So for an endothermic reaction, why does increasing heat, for example, shift the equilibrium to the right-hand side? According to reaction rate, if you can explain that. Does anyone want to give that a go? They asked that last year with the graph question.
Wait, sorry, could you say that again?
Yeah, I'll write the question for you so you can break it down. So your question could be, they'll usually give you a graph though. You won't get written questions like this. They want to make your exam, you basically, every year in the HSC, there'll be one question or two questions that no one has ever seen before in terms of graphs. So that's what I want you to be ready for, right? If you're using particle collision theory, explain why equilibrium shifts right-hand side when temperature is increased for an endothermic reaction. It'll be like 2 marks. This will usually be through a graph. They'll maybe give you a graph of an endothermic reaction and its enthalpy energy diagram, and then ask you to, with reference to the image above, justify or explain. So someone give me a verbal answer. Give it 10 seconds to just process and think in your head and give me a verbal answer. Okay, so let me ask Taha. Can you answer this one?
Not too sure.
Shushant?
I'm not too sure either.
Serene, any ideas?
I think I can. Oh.
Okay, Arik, whenever you're ready, take it away.
Is it something to do with activate energy?
Yeah, it definitely is something to do with that.
Increasing temperature of the system will increase the average K of both reactants and products. So the frequency of successful collisions where K is greater than activation energy will also increase. This increases both the forward and reverse reactions. However, since the forward endothermic reaction has a greater EA than the reverse exothermic reaction, the increase in temperature will result in the rate of the forward reaction being increased to a greater extent. This results in the equilibrium to shift right. So yeah, I mean
Pause for 1 sec, Arik. Just pause for 1
Yeah.
sec. I'm going to give you a little example, right, of what you said. This is an energy profile diagram. I'm just going to give you random numbers, right? So whenever you're stuck, use thought experiments. So let's say this is 10. Let's say this is 20. Let's say this is 30. All right, what's the activation energy for the forward reaction?
30 or no 2020.
I'd say it's 30. Activation
30.
energy is the peak of the energy profile diagram.
Yeah.
What's the activation energy for the reverse reaction?
30.
Yeah. So the forward and reverse reaction have the same activation energy, but you mentioned that the forward reaction rate and reverse reaction rate had different activation energies in your answer. So you're very close. It was very good. I'd probably give you everything.
I've been always like using that when it came to like those questions. And I've always like been like, yeah, like I haven't like I think I haven't like lost like 'cause I had that same question in my final exam, and yeah, I did like I did write that, and I did like get full marks in that.
Oh, really? Okay, your teachers overlooked it
Wait,
because
so I thought activation energy is the difference.
so activation energy is an absolute number, but I think what you're referring to is that energy required to reach activation energy is different for reactants and products. But if I ask you what is the activation energy for a reaction, it's just what is the energy that we need to reach to start breaking reactant bonds and begin the reaction. So it's 30 for both. Activation energy is fixed. Yeah, good. So Milith, you mentioned a very good point. Now, do you want to kind of clarify it? Do you want to continue off this? Increase in temperature increases the kinetic energy of your reactants and increases the frequency of successful collisions. What would you say next?
However, as a greater proportion of the reaction molecules reach the activation energy compared to the product molecules, this would lead to a shift in, this would lead to a favoring of the forward reaction.
Good, right? The way you think about this is since the products are already at such close energy to the activation energy, we can assume, let's say 90% of the products already have energy greater than activation energy. But your reactants have a much lower energy. So we can assume, let's say 10% of your reactants have energy greater than activation energy. So when you increase temperature, let's say 100 degrees, we'll go from 90 to maybe 97% of product particles having energy greater than activation energy. But we'll go from like 10% to let's say 70% of reactant molecules now having energy greater than activation energy. So do we see that what's happened now is proportionately increasing temperature for an endothermic reaction gives a greater proportion of reactant molecules the energy to overcome activation energy. So 60% more reactant molecules have energy to overcome activation energy, whereas only 7% more products had the energy to overcome activation energy now. right? So quite literally what you said, I would say, is a perfect answer. Great proportion of reactant molecules will now have energy that's greater than activation energy. Therefore, the forward reaction is favored as there is an increase in your reactant. There is a greater increase in your reactant collisions. Successful reactant collisions. And therefore, you will increase the forward reaction rate and shift to the right-hand side. Good. That's the principle there. Does that make sense to everyone? Right? So you just need to work on explaining that very concisely. So give it a go after class and explain it to yourself very concisely as well. Good. All right, good job. So next lesson, we'll probably quickly finish off mod 6 and we'll start looking at mod 7 and 8 combined. And I think the next 2 lessons or so, we can look at mod 7 and 8 combined. Okay, everyone? Good.